we've got to the time David decreed, so I'll start again. So the final part of this course, I'm supposed to talk about applications. And by applications, I guess I really mean to situations where we don't just have one L-adic representation, but we have L-adic representations for all L, for instance, if one starts with some geometric object. And in fact, the theorem 1 and 2 that David just talked about are exactly designed. I mean, we were searching for something, and this is what we finally found, that was both provable and had the property that whenever you have a compatible system, they should be applicable almost everywhere in the compatible system for almost all L. So to talk about this, I need to start by explaining what I mean by a compatible system of L-adic representations. And there's more than one. There's a whole series of slight variants of the definition you could make. And to be precise, I want to say what I'm going to mean. Of course, they should all be the same, but we don't know that yet, so I have to say what I mean. So I'm going to start with two number fields. And first of all, I'm going to define a weakly compatible system. So by a weakly compatible system R, consisting of R lambda, so there will be one R lambda for each lambda prime of M. So M will be sort of coefficients, lambda prime of M, of representations of the Galois group of F. We mean well, for each such lambda, R lambda will be a representation of the Galois group of F. Into GLN, it will have some dimension n, which will be independent of lambda. Let me say of the algebraic closure of M lambda. And this should be of the sort we've always been discussing: continuous, semi-simple, definiteness, and algebraic. So remember, by algebraic I meant that it's unramified almost everywhere at all but finitely many primes, and de Rham at all primes above the residue characteristic of lambda. And these things must be consistent in some way. And the first way they must be consistent is that at places that they're unramified, the characteristics of polynomials of Frobenius must be the same. So there exists a finite set S of bad places of F, such that if V is not in S, well, the representation should be unramified unless the residue characteristic of V is the same as the residue characteristic of lambda, where it should be the corresponding thing, which is crystalline. Then R lambda is unramified at V, and this is in the case V not dividing lambda not dividing the residue characteristic of V, and crystalline at V if lambda divides the residue characteristic of V. And this compatibility, and there exists QV of X, a polynomial in a variable with coefficients in M, which will be the common characteristic polynomial of Frobenius, such that QV of x is the characteristic polynomial of R lambda from V if lambda doesn't divide the residue characteristic of V. And I want a little bit more than that. I want also the Hodge-Tate numbers not to depend on the choice of lambda. So said more precisely, so for all embeddings Tor of the co of F into the algebraic closure of the coefficients, there exists a multiset Hodge-Tate Tor of the compatible system of integers such that for all lambda and all embeddings of m bar into m lambda bar over m, which sits in both these things, the Hodge-Tate of R lambda with respect to an embedding of m lambda, which way around am I trying to say it, alpha composed with Tor, that will give an embedding of f into m lambda, will be Hodge-Tate Tor of R. This is saying the Hodge-Tate numbers are independent of lambda. Okay. But sometimes we want even more, and I'll call it strictly compatible. If it satisfies these conditions, but it also, at the bad primes, there's the analog of this. So for all places V of F, there exists a Wedelin representation from a Wedelin representation of the V group of FV over m bar, which again is sort of universal for all these things, such that for all lambda not dividing the residue characteristic of V, a prime of m, and all alpha mapping m bar into m lambda bar, which is m linear, we have that if I take R lambda, restrict it to the decomposition group at V, take the corresponding Wedelin representation, that should be alpha of Wedelin V of the compatible system. So it's just saying that it's compatible even at the bad primes. There are other properties we will want to talk about of strictly compatible systems. Sorry.
Is that all finite places or all places?
Oh, that's a good point. All finite places. Prime, sorry. Of course, one could, I mean, as I say, there are infinitely many variations on this. I could ask this for the infinite places. I could allow lambda here. That would be even better. But because of guided by what we know about the L-adic representations attached to automorphic forms today, I'm going to stick with this. I'll call R pure. If it satisfies the usual condition.
So you don't assume anything that lambda dividing.
in this definition, I'm not saying anything about either the characteristic polynomial, about what the Wedelin representation there. It is crystalline at the places it should be. Almost all of these things are crystalline.
We don't assume that the proper use of the crystalline.
That's not in this definition. Of course, one might want to add that, yes. Okay, where have I got to? Sorry. It is pure of some weight W if the usual thing is true, is for all good primes and all embeddings maps M into C and all roots alpha of the image under this embedding of the characteristic polynomial of Frobenius. We have the absolute value of this root is the order of the residue field to the W. But I also want a bit more. I want also the weight should also be related to the Hodge-Tate numbers. So I also want to put that in. So I want the Hodge-Tate numbers at, well, let me say, for all Tor maps F into M bar, and for all C in the Galois group of M bar over Q, a complex conjugation, the Hodge-Tate numbers at C composed with Tor should be W minus the Hodge-Tate numbers at Tor. So the set of W minus H, where H is in Hodge-Tate Tor of R. And there's a sort of stricter version of this, so let me say R is strictly pure if it is strictly compatible and for all V, Wedelin V of R is pure, and I'm not going to go through. So that if n is 0 in the Wedelin representation, if it's just a representation of the V group, then that means that this is satisfied for the characteristic polynomial of any Frobenius lift, 1 and hence for all. And if there's an n, well, there's a similar definition. What else? I'll call, just by analogy with a single representation, I'll call R regular if for all Tor, Hodge-Tate Tor R has n distinct elements. So there are no repeated Hodge-Tate numbers. I will call R polarizable if there exists a compatible system of characters, one-dimensional representation, so I guess in this case I need F CM or totally real, and then I guess categorical system of characters of the Galois group of the maximal totally real subfield, such that for all lambda, the pair R lambda, mu lambda is polarized in the sense I gave a few weeks ago. There's a symmetric pairing under which the adjoint of R lambda sigma is mu lambda sigma times R conjugation of sigma by complex conjugation inverse. And One other thing I should say, I'll call R is irreducible. Well, again, it should be true that if one of the R lambdas is irreducible, they all are, and that should be the definition of irreducible. But because we don't know that, a convenient definition of irreducible for us will be if there exists a set L of rational primes of Dirichlet density 1 such that if lambda divides L in L, then R lambda is irreducible. So in a sense, if almost all of these things are irreducible in a suitable sense. Okay. If I have pi, so go back to the case F, Cm, or totally real, and if I have pi polarized or polarizable cuspidal, regular algebraic cuspidal automorphic representation of GLN of AF, then we know how to associate to a prime L and an isomorphism of C with QL bar, analytic representation. From the properties we stated about those at the beginning of this series of lectures, that immediately you see that they form a compatible system. So we get R pi polarized regular in fact strictly compatible, or even strictly pure. So strictly compatible and pure in the strong sense system of L-adic representations of the Galois group of F. So the precise definitions of pure and so on I made so that we actually know that. Let me fix an embedding of M into the complex numbers. When we get such an embedding, we can talk about, well, if R is pure, we can talk about the partial L function away from the bad primes of I of R of S, which is just defined by the usual sort of Euler product over V not in S of whatever it is on K2 is NS over the characteristic polynomial of Frobenius, thought of as a complex polynomial, the order of Kv to the S. Is that right? Yep. And this is converges in the real part of S greater than 1 plus W over 2 to a holomorphic function. If R is strictly pure, we can actually define the whole L function to be the product over all finite places of the usual L factor associated to Wedelin V of R, made a complex representation by I of S, which will again converge in the same region and again be holomorphic. And one can pretty nearly define, if I had in strictly compatible, if I'd allowed the infinite place, I could also at this point define the L function with its infinite factors and the epsilon factors. So I didn't do that, but at least if R is strictly pure and regular, then I can add the infinite factors and I can define the epsilon factors can be defined. The point is that the factors at infinity, the factors at the finite places even here only depend on W Vedelin V of R, the attached Vedelin representation. At the infinite places, they only depend on the pair of the Hodge-Tate numbers. That you don't need the whole representation of the infinite Ve group, the Ve group at infinity. You only need the Hodge-Tate numbers in the image of complex conjugation. We have the Hodge-Tate numbers, so you want the image of complex conjugation. So as I say, if I had some strict compatibility here, I could figure that out. In the regular case, the image of complex conjugation is at least conjecturally determined by just knowing what the determinant of complex conjugation is, which I do know. And so I can write down what should be I can write a formula which should give the correct factors at infinity. Okay, and before we leave just these generalities, I want one purely algebraic property of these weakly compatible systems, which will be extremely useful to us. Which roughly says whenever I have at least a regular weakly compatible system, you don't lose much information reducing mod L for most L. So, proposition, suppose R is a regular weakly compatible system. Then there exists L, a set of rational primes of Dirichlet density 1 such that if lambda is a prime of M dividing one of the primes in L, and if S contained in R lambda is an irreducible constituent of R lambda, then the reduction of S, mod S will preserve some lattice, I can reduce it mod L, will again be irreducible. And in fact, more than that, I can, if I like, before I take the reduction, I can restrict to the Galois group of the extension of F cut out by the Lth root of unity. So this extension does depend in a weak way on L. Okay, so in a regular weakly compatible system, you can tell what the irreducible components are somehow before or after reduction. For most L, it doesn't make any difference. So the proof is slightly involved. So I'm not going to, certainly not going to go through it in detail, but I did want to at least point out the main point. So I'm going to define RL to be the representation, the cyclotomic character. That's put in there because we want to know something about this cyclotomic field, plus the sum over lambda divide L of R lambda, and that will map GF to GL1 plus n times the degree of M over Q of QL. Okay? And I will let GL contained in this general linear group, there's a risky closure of the image of RL.
You don't mean QL, you mean QL bar, right?
No, here I do. Oh, you're right. Sorry, I should have said something. Almost the reason for saying regular here is that you can see in the regular case, I can replace m lambda bar here by m lambda. And once I've replaced m lambda bar by m lambda, I really can put QL here. Yeah, sorry. Because somehow, once it's regular, just locally at primes above L, you can see that the image of this, or the Lie algebra of the image of this, would contain an element with n distinct, with eigenvalues, essentially the eigenvalues being the Hodge-Tate numbers, rational over, which will be rational over m lambda or anything else. And so the image of this Galois group would contain an element with n distinct m lambda rational eigenvalues, and that's enough to prove that this whole thing can be defined over m lambda. Because I'm assuming everything inside is semi-simple, this will be a reductive group, maybe not connected, so I'll let GL0 equal the connected component of the identity in GL, so this will be reductive. I will let GL adjoint equals GL, the connected component, modulo its center. And I will let GL simply connected be the simply connected cover of GL adjoint. Okay. And the first thing to remark is that the extension cut out by the component group of GL is independent of L. So that's an observation of Serre, as there exists F naught over F, such that the Galois group of F naught over F maps isomorphically to GL modulo GL0 for all L. So that's the first very useful bit of information we have. And the second bit of useful information is a beautiful theorem of Michael Larson, which says the following: there exists a set L of Dirichlet of primes of Dirichlet density 1, as in the theorem, such that and for L in L, there exists an integral model for this reductive, for this semi-simple group. There exists a semi-simple group scheme let me say GL simply connected tilde over ZL with generic fiber GL simply connected. Such that the ZL points of this are essentially the image of the Galois group. So such that GL simply connected tilde of ZL is the inverse image of the image of the Galois group that makes sense, which is GF0. GF's write it here. So we have GL contains GL0, maps onto GL adjoint, which also comes from GL simply connected. We have the Galois group of F mapping into here by RL. This contains GF0, which will map into here by definition, and so we will also get a map from GF0 to GL adjoint. And if I take the image and then take its pre-image in here, I'll get just the integral points of this group is the inverse image, maybe I should say in GL simply connected QL of the image of GF0 in GL adjoint of QL. So the
In sales result, you really mean all L or almost all?
I think this is all L, isn't it? I think so, but I could check. Does somebody remember? This? No. I think I wouldn't swear to it because the argument's a bit long and complicated, but I suspect really the only place I'm using regularity is to ensure rationality at this stage. Sorry, we? Sorry?
You probably don't care.
I don't care. I certainly don't care for this, no. Okay, so this somehow translates the proof of this thing about Galois representations into really just a question about algebraic groups. So it becomes, after Michael's result, it becomes a sort of purely algebraic group question, which you might imagine one can solve, even if you don't immediately see all the details. Okay, so after these preliminaries, let me move on to the applications. So the first is a potential automorphy theorem for compatible systems. So suppose F is CM or totally real. And that R is, well, the usual things we want in everything we've been doing, a polarizable regular, irreducible, weakly compatible system of L-adic representations. Then, first of all, R is potentially automorphic, so there exists F primed over F, Galois CM extension. Such that the restriction of R to GF primed is automorphic. And the usual remarks that I had last week and David mentioned again this morning apply. I can assume I can arrange f primed over f to be linearly disjoint from any given finite extension of f, and I can ensure it's Galois over any subfield of f over which f itself was Galois. So plus usual remarks, sort of technically useful improvements. Secondly, this weakly compatible system is in fact pure and strictly compatible. So R is strictly pure. And as it's regular and strictly pure, I can define its L functions. They converge in some right half plane. So L I R, remember I is an embedding of the coefficients into the complex numbers, has meromorphic continuation to the whole complex plane, and the usual functional equation holds. So lambda I R of S is epsilon I R of S lambda I R dual of 1 minus S. Okay, well, what do we have to do to see this? Well, the first part, I'm just going to, so R will be a collection of R lambda, and I'm just going to apply it to some R lambda. So I'm going to apply David's theorem 2, I think, from earlier this morning, to R lambda for some lambda such that, well, the key thing that R lambda restricted to GF zeta L bar is irreducible. Maybe I also need lambda divides L, which is greater than 2n plus 1. These will all, there may be a few other conditions that exclude a finite number of primes, zeta L. I don't know where we need, yeah, something like this. And this theorem up here, well, by the irreducibility assumption for most lambda, excuse me, this will be irreducible, or this before I reduce it to G zeta L, and then this proposition says that when I form the reduction and adjoin the zeta L, I get, it remains irreducible. So that's easy. For this thing, I have f primed over f. I want to, this is a local condition, so I'm going to try and check it at some prime v. I get some prime w above v. I can look at the fixed field of the decomposition group at w. And I can check once once R is automorphic over f primed, this thing would likely not be soluble, but the decomposition group's always soluble, so this is a soluble extension. So once I know that R is automorphic over f primed, R will also be automorphic over E, so R restricted to G E will be base change will imply will be R pi E, some pi E. And now this will already contain all the information at what's going, so, and then Wedelin, so Wedelin V of R will be the same as Wedelin W of R restricted to GE And this will be independent. This would be independent. Well, I mean, so this thing isn't really defined until I know it's strictly compatible. But maybe what I should say is that Vedelene R lambda restricted to GFV will be the same thing as Vedelene R lambda restricted to GEW. And this is independent of lambda. So I get the strict compatibility, and it's also part of the theorem. This is also the reciprocity map applied to pi E W, which we know has to be pure, so we get the purity as well.
The red part, that's for W prime to L, or?
Yes, this is all for lambda not dividing the. Sorry.
The first line is true always, or?
Yeah, the first line's true always. It's just a Galois theory statement. And now the third part is a Brouwer induction argument, which is very common in applications of these potential automorphy theorems. So I should go through that. From Brouwer's theorem, the trivial representation of the finite group, the Galois group of f primed over f, is a sum, finite sum of integers times the induction from Gal f primed over ei, where f prime contains ei contains f, and this extension is soluble, in fact even nilpotent if you want, to the Galois group of f primed over f of some character chi, which is a character of f primed over ei to whatever m bar cross, if you like. So the trivial representation can be written as a virtual representation as the induction from soluble subgroups. And tensoring with r lambda for all lambda, I can move the r lambda into here, and I obtain, well, let me write it this way, r is equal to the sum as a virtual representation, sum over I ni times the induction from the Galois group of ei to the Galois group of f of chi I tensor r restricted to the Galois group of ei. But this we know, just as I had a pi e here, for each of these ei, I get a pi, so r restricted to gei will be r, the compatible system associated to some pi ei, cuspidal automorphic representation of gln aei. And so this thing is nothing else than the sum over I ni, the induction from gei to gf of chi I tensor the compatible system associated to the automorphic form, automorphic representation pi ei. And if I turn this into a question about L functions, I get L IR of S is the product. Oh, I've got too many I's. this will be an I without a dot, what the tech calls IMath, maybe. Product over I of the L function of, well, first of all, this thing, but this, the L function of the, will be the product over I of the L function of this thing to the nth power, but the L function of the induction is just the L function before I do the induction, and then this is an automorphic L function, so this is L pi EI. Takes the chi I composed with the Artin map of S to the Ni. So this has meromorphic this has holomorphic continuation to the whole complex plane. So this thing has meromorphic continuation, and the functional equation for this follows from the functional equation for these factors here. Okay. So the second application I want to talk about is fitting a single L-adic representation into a compatible system. So let's have FCM or totally real, as usual. I now need these. I'm going to start with a single L, so let me assume that L is a prime bigger than or equal to twice n plus 1 with n an integer. Assume that zeta L is not an element of F, so L prime n z. Let me assume that R mu is a polarized regular algebraic representation of G, L-adic representation of the Galois group of F in the sense we had before. And I want to assume, let's say, when I form the reduction and restrict to the cyclotomic field F zeta L, this is irreducible. So maybe I say suppose and then the conclusion is that it is part of a strictly compatible system. So then there exists a strictly pure system R of L-adic representations such that R is a member of one of the elements of this system. What are we doing? So let me at least sketch the proof. So we know by the theorem David described this morning, so R mu is automorphic over some F primed over F, Galois CM extension. And I can even assume that, let me write again GL for the Zariski closure of the image of R, and GL naught for its connected component, and let GL over GL naught come isomorphically by the Galois group of some F0 over F, I can assume that this is linearly disjoint from f0. So somehow the finite part of the image of is not going to change.
I'm a bit confused. Are you assuming anything about R? Like what's potentially diagonalizable or something?
Yes, I must be assuming, sorry, I must be assuming potentially diagonalizable. Thank you. Thank you. And again, I'm going to consider intermediate extensions which are soluble under f primed. And so R restricted to GE will be RL pi E some pi E for any such intermediate field by base change, and exactly as we just had. And I'm going to write again, well, let me just have Ni, chi I, and Ei as above. And I use Brouwer's theorem. And we know that R as a virtual representation is the sum over I, Ni, the induction from GEI to GF of chi I tensor R restricted to GEI. And that's a part of this thing associated to pi EI. So I'm going to try and define R to be the sum over I of Ni times the induction from GEI to GF of chi I tensor R pi EI, compatible system associated to pi EI. So certainly R will be a member of this compatible system, but this is not really a compatible system of representations. It's a compatible system of virtual representations. And what I know one element of it is actually a true representation, and I have to prove the other elements of it are true representations. So I don't really have time to go through this. So given some prime lambda primed, I don't know that R lambda primed pi f primed is irreducible in general, but I can write it as a sum of irreducibles. And it's not difficult to see that because I've stayed away from this extension f0 over f, and because of Serre's result of the independent of the group of connected components with L, that this in the same way f primed over f or f primed over EI is going to stay away from the group of connected components of the image, of the Zariski closure of the image of these things. So you can deduce that R lambda primed pi E for any of these intermediate fields over which f primed is soluble is the sum over the same A of R lambda primed pi E. A? And then somehow our element, if R is going to be a system of R lambda, then we see that R lambda is a direct sum of R lambda A, where each R lambda A is actually gotten from irreducible things, is a sum over I, Ni, induction from GEI to GF of chi I tensor R. Sorry, this is lambda primed. R lambda primed pi EIA. Sort of eighth part of it. As virtual representations, and it will enough to show that each of these is a true representation. And to do that, this had better be, if it's a true representation, it had better be irreducible, because its restriction up here is already irreducible, so these were chosen to be the irreducible constituents up here. So you need to calculate R lambda primed A, R lambda primed A. Usual pairing on the Grothendieck group. So any bilinear pairing, an irreducible representation with another one is either 0 or 1, depending whether they're isomorphic or not. If we can show this is 1, then this has to be a true representation. So sufficient to prove that this thing is 1, and then this is a true representation. But the point is, using Mackey's, these are using bilinearity, you reduce to looking like things, the induction of something times the induction of something else. Find the pairing here. By Frobenius reciprocity, this is something like A times the restriction of the induction of B. By Mackey's theorem, the restriction of an induction is the sum of the inductions of some sigma applied to conjugation by sigma of some restriction of B. And then again, by Frobenius reciprocity, this will be a sum of the thing's restriction of A times the sigma of the restriction of B. And now, when we had inductions, we might have been over fields that weren't soluble inside F prime, but at this stage, everything in sight will be defined over a field which is soluble inside F prime, so everything in sight will be related to an automorphic form, so we can evaluate the products we get there, and putting everything back together, we do indeed conclude this.
So are you using the residue of the L function in the last step? So we can the automorphic.
I'm not sure that well, I can do if we need to, but I'm not sure that I do, because these will both be irreducible representations of sort of like looking a bit like this, and I'm not sure one can't do it all on the or on the Galois side somehow, but I'm not 100% sure. No, because I don't know that. I had to split it.
I mean, you start from something defined over F.
That's a good question. Let me, because I'm essentially out of time, let me try and answer that question afterwards to anybody who's interested. Let me finish by just stating one more theorem for completeness' sake. So the final theorem is a irreducibility condition. So let's have F a CM field, pi chi polarized regular algebraic cuspidal automorphic representation of GLN of AF. And I want to assume that pi e is what we call extremely regular, which, if you like, is the following, i.e. there exists Tor maps F into C such that, with the following property, such that if H and H primed are two subsets of the Harris-Chandra parameters at Tor for pi infinity, remember this is a set of n integers with the same cardinality, and if the sum of the elements of H is the sum of the elements of H primed, then H equals H primed. So in some sense, the spacings between the weights really have to get bigger and bigger or something like that. So this is a very strong condition, but it does happen. And then the conclusion is that the L-adic representations associated to pi are almost all irreducible. So then there exists, well then, the compatible system associated to pi is irreducible, meaning that for almost all for a set of rational primes of Dirichlet density 1, the elements of this lying above one of those primes will all be irreducible. And this is proved by looking at the L functions. You're going to look at the L function of R pi tensor R pi joule of S. The order at S equals 1 of that is -1 because it's the same as L pi cross pi joule S. And on the other hand, if RL pi is RL pi 1 plus RL pi t or something, then we show that each of these, this condition will in fact imply that each of these has to itself be conjugate self-dual. So applying, for most L, applying the potential automorphy theorem, each of these factors will be automorphic coming from something else, and then one can write this L function as a product of the L functions of the associated to the L functions associated to the product of an automorphic form associated to this with an automorphic form associated to this. Again, we have to use a sort of Brouwer induction argument because those things will only be defined in some extension, and you'll see that this is -t, at least for most L. So you see that there has to be just one component. Sorry, that's a bit sketchy, but I don't have time for more. So I guess I'll stop there, and if